Hello everyone, good evening. Here we shall solve some KCET previous year questions from the chapter Nuclei. So any doubts if you have in any steps of the solutions, then write that in the comment section so that we can clarify them in the subsequent videos. And in any other chapter of physics, if you feel more difficulty, then also write the name of that chapter in the comments section. Then we shall give more clarity on it and solve more and more questions on that chapter. And in any other chapter of and some more important homework questions will be uploaded in the Sapience education application on every chapter based on the previous year KCET exam. So please install our Sapience education application, whose link has been provided in the description. So here in this chapter, nuclei, we shall solve from the first question. It is told that the ratio of the nuclear radii of elements with mass numbers 216 and 125 is. So we know that the radius of a nuclei that is proportional to the cube root of the mass number. So therefore, the ratio of the nuclear radii R1 by R2, that is equal to A1 by A2 whole power 1 by 3, means the cube root of this. So that is equal to 216 by 125 whole power 1 by 3. So it means we have to find the cube root of 216 divided by cube root of 125. The cube root of 216 is 6 and cube root of 125 is 5. So the answer is 6:5. Option A is the correct one. Then question number 2, it is told, on bombarding uranium-235 nucleus by slow neutron, 200 mega electron volt of energy is released. If the power output of atomic reactor is of the atomic reactor is 1.6 megawatt, then the rate of fission will be. It means the rate of fission, it means that how many fission reactions are happening per second. So the power output means it is the energy output per unit time. It means this much of energy. Therefore, 1.6 megajoule of energy is released per second. Megajoule is the energy output. Per second. So it means what? It means it is 1.6 into 10 power 6 joule. And for one fission reaction, the amount of energy that is released, that will be, and the amount of energy released per fission reaction amount of energy released per fission reaction, that is equal to 200 mega electron volt. So which is equal to 200 into 10 power 6 electron volt, and 1 electron volt means 1.6 into 10 power minus 19 joule. So it means this will be 1.6 into 2 into, I can write this is 10 power 8 minus 19 joule. So it means that 2 into 1.6 into 10 power minus 11 joule is the amount of energy released per fission reaction. Therefore, the number of fission reactions that is happening per second. Therefore, the number of fission reactions happening per second. The number of fission reactions happening per second, and that is also equal to the rate of fission. that is equal to this energy output per second divided by the amount of energy released per fission reaction. So that is 1.6 into 10 power 6 joule divided by is 2 into 1.6 into 10 power minus 11. So this 1.6 will cancel, and then you can write this 10 power 11 plus 6, that is 17 by 2. So this is 10 by 2 into 10 power 16 I can write. So this is 5 into 10 power 16 per second. So these many fission reactions are happening per second. So it means option D is the correct one. Then in question number 3 it is told the masses of two radioactive substances are same. The masses of two radioactive substances are same and their half-lives are 1 year and 2 years respectively. The ratio of their activity after 6 years will be. The masses of two radioactive substances are same, M1 equal to M2. Their half-lives, the half-life for the first one, that is 1 year, the half-life for the second substance, that is 2 years. The ratio of their activities after 6 years will be. So the masses of two radioactive substances are same. So therefore, initially, suppose they have the same number of radioactive nuclei. Suppose they have the same number of radioactive nuclei initially. Therefore, D, we can write dN1 by dt, that is equal to minus lambda 1 N1, and dN2 by dt, that is also equal to minus lambda 2 into N2. We have the same number of radioactive nuclei initially. So we know that T half, that is equal to ln2 by lambda. We know that n1, if we solve it, this will be n0 e power minus lambda 1 into t, and similarly n2 also will be equal to n0. So here we have assumed, suppose they have the same number of radioactive nuclei initially. It means that both have initial number of nuclei as n0. n0 will be, so n2 will be n0 e power minus lambda to t. Therefore, after 6 years, N1, so the ratio of the activities at has been asked. So activity 1 by activity 2. So activity 1 will be lambda 1 and 1. Activity 2 will be activity of the substance 2 will be lambda 2 into E2. So n1 that will be equal to n0 e power minus lambda 1 is ln2 by t half, ln2 by t half, first one, that is 1 year, and this is into 6 years. So that is n0 e power minus 6 ln2, that is n0 e power ln2 power minus 6 is 1 by 2 power 6. 1 by 2 power 6 means 64. 1 by 64. This is n0 by 64. And similarly n2 will be n0 e power minus lambda 2 into t. So after 6 years this will be n0 e power minus ln2 by lambda, which is ln2 by 2 year into 6 years. This is 2 3 6. n0 e power minus 3 ln2, ln2 power minus 3, that is 1 by 8. So this is n0 by 8. Therefore, the ratio of the activities after 6 years, that will be A1 by A2, that is lambda 1 N1 by lambda 2 N2. Lambda 1 is ln2 by t half, so ln2 by 1 year into this is n1, that is n0 by 64. This is ln2 is means lambda 2 is ln2 by 2. This is n0 by 8. So this will come n0 ln2 will cancel out. So this is 1 by 64 into 2 with your 16. This is 4 to 64. So this is 1 by 4. That is 1 is to 4. So option C is the correct answer. Then in question number 4, it is told uranium 235 undergoes successive disintegrations with the end product. Uranium undergoes subsequent disintegrations with the end product as phosphorus 203, 82 203. The number of alpha and beta particles emitted are so here from uranium 235, suppose n number of alpha particles are emitted. It means that it will be NHE24 plus suppose n number of beta particles are emitted. So this will be beta, which is E minus 1 0 plus it will be phosphorus 82 3. So therefore the net charge should be same. So therefore 2n minus m plus 82, that should be equal to 92. So it is the equation 1. And also the total mass should be same. That is 4n means the total number of nucleons should be same on both the sides. that is 4n plus m into 0 plus 203, that is equal to 235. So this is equation 2. From here we can see that 4n plus 203, that is equal to 235. So therefore 4n is equal to 32. Therefore n is equal to 8. So therefore 8 alpha particles are emitted. Then 2 into 8 minus m plus 82, that is equal to 92. So therefore 2 is 16 plus 82 minus 92, that is equal to m. Therefore m will be equal to 6. So therefore here 8 alpha particles and 6 beta particles are emitted. So option A is the correct answer. In question number 5 it is told, in a radioactive disintegration, the ratio of initial number of atoms to the number of atoms present at the instant of time equal to its mean like this. So so mean lifetime means what? Mean lifetime is so at t equal to mean life, the number of nuclei is equal to n naught by e. So the mean life is given as 1 by lambda. The ratio of initial number of atoms to the number of atoms present at the instant of time equal to its mean life. So therefore we have to find n naught by n. So that is equal to e. So therefore option C is the correct answer. Question number 6 it is told, the beta decay means emission of electron from beta decay means emission of electron from the outermost electron orbit, stable nucleus, or an outermost electron orbit. So the beta decay means emission of electron. Beta decay means emission of electron from a radioactive nucleus. So option D is the correct answer. In question number 7 it is told, the phenomena in which proton flips is called nuclear magnetic resonance. Option A is the correct answer. Question number 8 it is told, assume the graph of specific binding energy versus the graph of specific binding energy versus mass number is as shown in the figure. Using this graph, select the correct choice from the following. The graph of specific binding energy versus mass number is as shown in this graph. Specific binding energy, it means binding energy per unit nucleon. Fusion of two nuclei of mass number lying in the range 100 to 200 will release energy. So here the binding energy is high. So here the fusion of the nuclei of mass numbers, fusion of two nuclei from 1 to 50 will release energy. Yeah. So fusion of nuclei of mass number lying in the range 51 to 100 will release energy. Since why here the binding energy per unit nucleon is less, it means it is less stable, but these nuclei from mass number 100 to 200, these are more stable. So when these will fuse from 1 to 50, these will fuse, then it will form from 51 to 100 and this range, when they will fuse, then they will form some nuclei which is in then it will form some nucleus which is in this range from 100 to 200. So when this fusion will happen, then it will form more stable nucleus, and when more stable nucleus is formed, it means that it is having more specific binding energy, and it will release energy. So option B is the correct answer. And from 1 to 50 if I take, then if it gets fused, then again the nucleus which will be formed, that will also lie in the range from 51 to 100 only. So its stability is same as that of 1 to 50, so it will not release any energy. So from 51 to 100 only, if we choose any two nucleus, then that will fuse and release energy. Then in question number 9, it is told, pick out the correct statement from the following. Energy released per unit mass of the reactant is less in case of fusion reaction. Then packing fraction may be positive or may be negative. Plutonium 239 is not suitable for a fusion reaction. For stable nucleus, the specific binding energy is low. No, it is false. Specific binding energy should be high. Stable. Now here, the packing fraction may be positive or may be negative, but packing fraction should be positive always. So means that option B is the correct answer. In question number 10, it is told a radioactive sample S1 having the activity A1 has twice the number of nuclei. Radioactive sample S1 having the activity A1 has twice the number of nuclei. It has twice the number of nuclei as the sample S2 of activity A2. So a radioactive sample S1 has the number of nuclei, it has S1, as suppose N1. That's twice the number of nuclei of another sample S2. It means N1 is equal to 2N2 and A2 is equal to 2A1. Then the ratio of the half-life of S1, the ratio of the half-life of S1 to the half-life of S2, that is how much? That we have to find. So this is equal to ln2 by lambda 1 divided by this is ln 2 by lambda 2. So it means we have to find lambda 2 by lambda 1. That value is fine. Now here a2, so from here I can say therefore a2 is lambda 2 n2, that is equal to 2 into lambda 1 n1. Into lambda 1 n1, and n2 is n1 is equal to 2 n2. So therefore I can say ln2 n2, that is equal to 2 lambda 1 to 2 n2. So n2 will cancel. Therefore lambda 2 by lambda 1, that is equal to 4 by 1. So the ratio is coming 4. So option A is the correct answer. Question number 11, it is told when a neutron is disintegrated to give a beta particle, when a neutron is disintegrated to give a beta particle which is E0, E minus 1, 0, then proton is also emitted, proton which is H11, that is also emitted, and one anti-neutrino is also emitted. So it will emit a proton and an anti-neutrino. So option D is the correct answer. In question number 12, it is told that a thermonuclear reaction of hydrogen inside the stars is taking place by a cycle of operations. The thermonuclear reaction of hydrogen inside the stars is taking place by a cycle of operations. Thermonuclear reaction of hydrogen inside the stars is taking place by a cycle of operations. The particular element which acts as a catalyst is carbon. So carbon acts as a catalyst. So option D is the correct answer. In question number 13, it is told the fraction of the initial number of radioactive nuclei M0 which remain undecayed after half of a half-life, remain undecayed after half of a half-life of the radioactive samples. Half of a half-life means half-life is ln2 by lambda. So half of half-life means T is equal to half of ln2 by lambda, which will remain undecayed. It means the number of radioactive nuclei that has decade at time t, that is given as n is equal to n naught e power minus lambda t. So for half of half-life, that will be equal to n naught e power minus lambda into ln2 by 2 lambda. Lambda will cancel, so this is n naught into e power ln 2 power minus half, so it is 1 by root 2. This is equal to n naught by root 2. So therefore, the fraction of the initial number of nuclei which so the fraction of the initial number of nuclei. It means that 1 by root 2 times of the initial number of nuclei, that will remain undecayed after half of half-life. So the answer is 1 by root 2, which is option D. Then 1 Curie represents 1 Curie equals to 3.7 into 10 power 3.7 into 10 power 10 disintegrations per second, or I can say this is equal to becquerel. So 1 becquerel is equal to 1 disintegration per second. So 1 Curie is equal to 3.7 into 10 power 10 disintegrations per second. So option D is the correct answer. 15th one is the radius of the copper 2964 nucleus in Fermi in how much? So we know that R is equal to R naught A power 1 by 3. So that will be equal, so for copper the radius will be R naught, which is 1.2 into 10 power minus 15 meter into A, the mass number is 64, whole power 1 by 3. It means you have to find its cube root, which is 1.2. So 1 Fermi is 1 Fermi means is 10 power minus 15 meter. So this I can write as 1.2 Fermi into this is 4 cube. So 4 power 64 power 1 by 3 is 4. This is 4.8 Fermi. So option A is the correct one. And in question number 16, it is told in a radioactive decay, an element XZA emits 4 alpha particles, 4 alpha particles, He24, plus 3 beta particles, which is E minus 1, 0, and 8 gamma photons. 8 gamma photons. Then the atomic number and mass number of the resulting final nucleus are. The atomic number and the mass number of this nucleus is how much? What do you have to find? So therefore Z will be equal to 4 to the 8, then minus 3, that is equal to 5, and mass number will be equal to 4 into 4, that is 16, plus 3 plus 3 into 0, so that will be 16. A is equal to 16. So option C is the correct answer. Then in question number 17, is told a radioactive nucleus has specific binding energy E1. It emits an alpha particle. The resulting nucleus has a binding energy E2. Resulting nucleus, suppose A, suppose A1, or I can say like X. Let the resulting nucleus be X. So it emits an alpha particle, which is He24, and plus it gives out some resulting nucleus Y. The specific binding energy for X, that is E1, means the energy per unit nucleon, and in Y also the energy per unit nucleon is E2. So then, therefore, so a less stable nucleus will undergo disintegration and it will form a more stable nucleus. So a more stable nucleus is formed. That means that E2 will be greater than E1. So option C is the correct answer. Then in question number 18 it is told the decay constants of two radioactive samples A and B. The decay constants for constant for A is 15x and the decay constant for B, that is 3x. They have equal number of initial nuclei. So both of them have equal number of initial nuclei, which is n0. Then the ratio of the number of nuclei left in A and B. The ratio of the number of nuclei left in A and B after a time 1 by x. Suppose we have to find n1 by n2. The ratio of the number of nuclei left in A and in B after a time 1 by 6x. So n1 will be n0 e power minus lambda 1 into t, and this will be n0 e power minus lambda 2 into t. We have to find its value at t equal to 1 by 6x. So this will be n0 will cancel, and this I can write e power lambda 2 minus lambda 1 into t. So this will be equal to e power lambda 2 is 15x minus this is 3x, sorry, 3x lambda 2 is 3x minus 15x into t, that is 1 by 6x. So this is e power minus 12x by 6x, which is e power minus 2. So option B is the correct answer. So here option D is the correct answer. Then in question number 19 it is told mass numbers of the elements A, B, C and D are 30, 60, 90 and 120 respectively. The specific binding energy of them are 5 megaelectron volt, 8.5 megaelectron volt, 8 and 7 respectively. Then in which of the following reactions energy is released? So the specific binding energy for B is the highest. So B is most stable. So D is less stable than B. So D is less stable than B. So in this energy will be, so this here energy will be released. Here energy will be released since D is less stable. And C is going to B plus A. C is going to B plus A. So here C, the specific binding energy of C is 8 megaelectron volt, but specific binding energy for B is 8.5. So it is going from less stable, so it is going from more stable to less stable, which cannot happen. So here energy is not released. And when it goes from B to 2A, so here more stable cannot go to less stable. So here also energy is not released. So only in the first one energy is released. So option A is the correct one. That means the rule is that energy will be released only when if a less stable nucleus, having less value of specific binding energy, only if a less stable nucleus goes to a more stable nucleus. So more stable nucleus means which has more value of specific binding energy. Okay, then in question number 20 it is told, pick out the correct statements from the following. Electron emission during beta decay is always accompanied by neutrino. Electron emission, so when beta decay is here, so with that one anti-neutrino is produced. One anti-neutrino will be obtained. So the first statement is wrong. Then nuclear force is charge independent. Yeah. So the same nuclear force will exist in between neutron and neutron, and between neutron and proton also, and between proton and proton also. So it means that the nuclear force is independent of the type of charge. So only if the neutron and proton are inside the nucleus, so only within the nuclear range the nuclear force will act, and that will act in between protons also, and in between neutrons also, and in between a neutron and a proton also. Then fusion is the chief source of stellar energy. Yeah, it is also true, since in all the stars and in the sun, the nuclear fusion is the only source of heat and light energy. So only 2 and 3 statements. So only the statements 2 and 3 are correct. Only the options 2, only the 2 and 3 statements are correct statements. So option D is the correct answer. Okay. So here we shall end the first part of this video on the chapter Nuclei. So hope all of you have understood the solutions of all these 20 questions. So in the next part of this chapter, we shall start from question number 21 onwards. And so any doubts if you have in these steps, then please write that in the comments section, and please install our Sapience Education application, where we shall upload some important homework questions based on the previous year KCET exam on every chapter. So thank you everyone. Bye.